fracture. Okay. So what the summarized thought is when they quench very quickly, okay, what they also want, so the surface, okay, I'm going to draw another section over here. And I'm going to shape this section. Okay. They want the surfaces to be in martensite, which is hard and brittle. At the core, so this is at the surface. At the core, they want ferrite plus cementite. Right? So the martensite is the one that carries the sharpness of the sword, the hardness of the sword. Whereas the ferrite and cementite, more of ferrite, okay, able to absorb impact loading. Okay, so it's not easy to, yeah, they discovered this long time back. Okay, so that's very intelligent of them. So that's why the sword is both what? Sharp, hard, and what? Tough. Okay, so it's not just cosmetic. Is normalizing above the annealing, or does it? Yeah, it has to be above. Okay. If you ask me why sunshine, I have not a freaking clue. Okay, but it's always deemed to be higher than the annealing temperature. Okay. Now you can go much higher. Okay, but remember what I told you. The higher the temperature you heat up to, it takes longer time to cool down. It also will have tendency to form crack formation, okay, or part distortion. So I cannot give you a range of numbers. It all depends on your part, the size of your part, okay? Let me see any other mind-boggling question, okay? I do apologize for not answering it earlier, okay? My bad. Anything, just type in, okay? Right. So next, we were talking about normalizing, okay? So there is a sword. So let's look at normalizing. Okay, so in normalizing, as you can see over there, okay, regardless of the percentage of carbon, right? Okay, regardless of the percentage of carbon, okay, the material has to be heated up to a single phase austenite. Okay, regardless of your carbon. Okay, and then the temperature. Okay, so you can see every time it is in the what? In the single phase austenite. Okay, so the temperature, I'm going to write this down. Okay, the temperature. Okay, temperature for normalizing is usually higher. Okay, usually higher when compared to full annealing. Okay, and in normalizing, that's a good thing about normalizing the good thing. So in normalizing, okay, the cooling process is CNC. Okay, it's what we call CNC. Okay, any idea what is CNC? Anyone?
Computer numerical control.
Well done. It's known as completely no control. Okay, so yeah, right. Okay, CNC is computer numerical control. Okay, but for this case, it's completely no control. Sometimes CNC machine is also completely no control. Okay, you crash the machine completely no control. So the cooling is done. Okay, is done. Is carried out. Is done in the atmosphere. Oh yeah. So you just heat it to austenite. You bring it out. Okay, you cool it out there. Okay, it does affect your properties. Okay, later on I'll tell you when we make landing gears. Okay, I was consulting a landing gear company, and they realized that in winter when they produce the landing gear, and in summer, okay, the process path is very different. Okay, and is no rocket science. It's nothing difficult to explain what's going on. Okay, so the thing about normalizing, okay, you have, regardless of the percentage of carbon, you have to heat up to single phase. Okay, the other thing that is good advantage is the cooling is done in atmosphere. Okay, so control cool, as you can see down here when I draw these lines, okay, it's done in a furnace. Okay, which I will elaborate later on. And it's not cheap. Okay, so you have to step down your temperature. You have to ensure that the entire part has the same temperature at the surface and then at the core. Whereas for normalizing, no, you just austenite, you hold at austenite temperature, the entire workpiece is austenite, put it out, let it cool in the environment. Okay, so you just need land, not length, land. Okay, place to store your material. So let's look at the cooling rate. Okay, let's look at the cooling rate. Okay, let's look at the cooling rate. Okay, so we are going to have I'm going to draw a box. Okay, so I'm going to label A, which is the surface. Okay, then I'm the next one, B is at the core. Okay, so one is the surface and the core. Then I'm going to draw a temperature time graph. So where is my lecture now is I'm highlighting the difference between full annealing and normalizing. That's where we are now. Okay. So this is temperature. This is time. Okay. So I'm going to write out a few. So 100, 200, 300, 400, 5, 6, 7, 8. We'll do up to 900. Okay. So if we were to carry out normalizing, okay, if we were to carry out normalize, the surface will cool very quickly. Okay. So this is A, which is at the surface, and this is normalizing. And then the core, depending on the size of your workpiece, okay, it tends to have a slower cooling rate. Okay. So this is B for normalizing. Okay. So for full annealing, right? For full annealing, and I'm going to do the surface first. Okay. So for full annealing, the temperature is lower. Okay. And then you bring it down in stages. Okay. So it's like a staircase. Okay. So you bring down. I don't have enough space, so it goes down to room temperature. It goes down to room temperature. Okay. So this is our A for full annealing. So what determines the step? Okay, you have to ensure that the surface and at the core are at the same temperature. Then you can bring it down. Let me elaborate one. So I'm going to use a different ink. So this is 800 again. So this represents the temperature of the core. Okay. So I'm going to draw this in green. So B for full annealing. Okay. So only when the temperature is at the surface and the core are the same, then it will go down like this. Only when it's the same, okay? And it is slower than the surface because it takes time to cool, right? Okay. So that is the step. So A is for the full annealing, the temperature profile of the full annealing, and B is for the core full annealing. Okay. As I said, both of them, as I said, I don't have enough space. If I have, it all has to come down to room temperature. Okay. So this is the difference in temperature profile, okay, of the material. Okay. So I'll write out what are the reasons to normalize steel. Okay, so which will you use, full annealing or normalizing? And I want you to know when to use what. Okay, and also will show you some stress profile based on carbon when you normalize steel and when you do full annealing. Okay, so the reason to normalize steel. Hold on, I have a question. Yes, martensite is hard and brittle. Samuel, you are right. Samuel, does that answer your question, or you have a follow-up? Cementite is also hard and brittle. Okay, Samuel. Okay, I have no reply from Samuel. I think he's okay. Right. So next we are going to go for the reason